Lab 4's goal was to observe the motion of a mass oscillating at the end of a spring similar to the motion of an extreme rope swing. This was done through analyzing a video of oscillation and inputting position data into a GlowScript code to create a model of the motion. Creating the model relied on two important physics principles, Newton's second law and the energy principle. These position and energy graphs were yielded at the end of the experiment and will be discussed in further detail later. However, it was concluded from the graphs that the system had no change in total energy. The experiment part of this lab consisted of releasing a mass on a spring at a certain stretched length and recording the following motion and position at each frame of the video. The system consisted of the spring and mass at the end with everything else as the surroundings, and the initial conditions were found to be a position of negative 0.124, negative 0.634, and 0 meters, a mass of 0.402 kilograms, and a velocity of 0. The video consisted of one frame every 0.095 seconds. Using Tracker, the mass's position was noted at each frame, and the X and Y positions were recorded in an Excel sheet. From the data that Tracker yielded, the period of oscillation was determined to be 1.519 seconds. This was found from matching trough to trough of the graph in Tracker. Once the position data was recorded and converted to the right format, it was input into a code designed to simulate the experiment. Using the equation 4 pi squared times the mass over the period squared, the spring constant was calculated to be 6.878. Knowing that at a relaxed length the spring would have no net force on it, the magnitude of the force of gravity must be equal to the magnitude of the spring force. With that knowledge, the relaxed length, L0, could be determined. The force of gravity is mass times the acceleration due to gravity, and must be equal to the force of the spring, which is negative k times L minus L0. Rearranging the equation gives L0 to be equal to 0.127 meters, and the rest of the computations in the code relied on Newton's second law and the energy principle. First, the two forces being considered were calculated using their definitions, and then, using Newton's second law, the net force was determined. The law was further applied to update both the position and velocity using the momentum principle and the update formulas. Finally, the length and direction of the spring were found using vector functions, and S was calculated by the equation L minus L0. In order to calculate the values to output on the energy graph, the energy principle was used within the code to determine all of the energies present in the model. First, the initial energies were calculated using the definitions known. Kinetic energy was determined by 1/2 mv squared, gravitational potential energy was found from mgh, and spring potential was calculated by 1/2 ks squared, with s being the value determined in the previous part of the code. The energy principle then dictated that the total energy be the sum of these individual energies. These calculations were later repeated in the loop, with the only difference being the addition of the change in energies found from final minus initial. In the end, the code yielded these graphs and simulation. Looking at the energy plot created by the code, you can see that the model does in fact satisfy the energy principle, as the total energies add up to 0, which equals the work done by the surroundings in the model. The total energy has a straight trend line along the 0 value, and each energy cancels out the other energies in the opposite direction. When estimating the oscillation period, one was taken from the x positions and one was taken from the y, and both were found to be equal to 1.519 seconds. This technically makes both accurate estimates, however the y position one should be used as it is in the same direction as the stretch of the spring. Potential sources of error. The graph shows some clear but minor discrepancies between the model data and the experimental data. This could have been due to mistakes in marking the center of mass in Tracker, not taking into account any work done by the surroundings, like air drag, or a slight error in period estimate.